Well, as you can see from here, epsilon naught is really boring. I mean, how many times do we really work in a vacuum? Like right now I'm not talking in a vacuum because I did. What I said was you wouldn't hear anything because it'd be a vacuum. So we want to spice things up a little bit with epsilon. First of all, we're going to epsilon naught. First of all, we're going to replace epsilon naught by epsilon. So remember that epsilon, farads per meter, it's a capacitance per unit length. So we're no longer in a vacuum, but we also want to put in some what? What else should we put into this epsilon here to make it more interesting?
To make it more interesting. Well, it's going in various kinds of materials, right?
Right.
And materials might be conductive, right?
Yeah, and what happens when you put a current through a conductive material?
Then there's power going through.
There's power going through and the material's going to heat up, so we get loss. So it'd be good, let's not have this boring business, right?
Yeah.
So, but how are we going to do that? Are we just going to add it in like adding salt in soup?
Oh, is that not how it works?
No, you got to go to the equation that has epsilon in it. Which equation is that?
That's not what I signed up for. Oh, sorry, what was the question?
What equation has epsilon in it?
The Faraday's law?
Faraday's law. Well, let's see. Does it? Are you sure?
Now that you ask me, maybe the Ampere's law.
Oh, yeah. I think it's Ampere's law. Curl of H is equal to, we got to add something. So that's where our salt will come in, whatever it is, in a minute. And this is what we had before. All right, so let's look at units. The units of this are 1/meters, and this is amps per meter. So this is amps per meter squared, and that's this kind of thing. Amps per meter squared is current density. So the units of this are amps per meter squared. So will the units of this be amps per meter squared. And we want to put in some loss. So what do you suggest?
Well, we're thinking of conductive materials, so there's some sort of conductance.
Conductivity,
Yeah, conductivity. So sigma.
Right? And what else?
Then you have some voltage across it, some E field. So let's say E.
Okay. Put on the vector there.
Oh, yeah.
Okay, now this is a current density, J. So J is sigma E. So let's just write that down here. J that we're going to add in, this J here, that is sigma E. Now, J equals sigma E is a famous equation if we think of standard circuits. So J and E and sigma, what's it going to be if we were thinking standard circuits?
Well, how many laws are there in circuits, right? Let's take a shot in the dark. Ohm's law.
Yeah, but J would correspond to?
Would correspond to current.
Right. And E corresponds to?
Voltage.
So sigma, of course, would, as you said earlier, correspond to 1/R conductance. So this is the vector form of Ohm's law. Now, if we want to see how epsilon changes when we introduce sigma in here, why don't we, what's the next step?
Why don't we just put them together and see what happens?
Yeah, but in order to put them together, I got to eliminate this time derivative here.
Oh, that's tough. Then what about consulting the other equations and plug in what this was, the phasor form?
Let's go to phasor. So let's write this in phasor form. Curl of H S e to the j omega t equals sigma Es into that plus, now when we do phasor, of course, the time derivative brings down a j omega, so we get j omega epsilon Es. Hey, this is cool. So let's combine the terms. Now, I want to write this somehow that this is going to be j omega epsilon effective.
Well,
What
let's
do you
try
do?
to equate them.
Well, let's try to, shall we factor out a j omega here, combine, and then see what that is? And then you can
Yeah.
write the answer up there.
In fact, let's show more steps than that and
Sure,
just go
let's-
through it. So j omega E effective, epsilon effective, is this thing, right?
Yep.
Oh, I'm going to run out of space again.
No, just put in plus sigma.
Plus sigma.
Now, continue down over here. Just
Mhm.
move it over a bit. Equals, or epsilon effective,
Equal, so you dump this over and get epsilon plus sigma over j omega. Then j, you move j up,
Yep.
and you would get sigma plus, minus.
Here, I got it.
Oh, thank you. J sigma over omega.
Wow. So there we have our epsilon effective.
Mm-hmm.
So we have the effect of storage,
Mm.
epsilon, and we have loss. But there's a frequency
Dependence.
term.
Mm.
So one of the things when we're looking at stuff, we're looking at what's going on in real life. And of course, the sigma is really important because if you have too much loss, you're not going to get any power delivery. So the real measure is how does this affect the intrinsic impedance?
Mm.
So
okay.
before we had, there it is, and we had a naught here, but I'm not going to put in a 0.
Mm-hmm.
I'm going to assume that our intrinsic impedance is mu naught. Now, when I say mu naught, we're basically saying a non-magnetic material. So that's usually the case in many applications. And now, instead of epsilon naught, we're going to put this in.
That spices things up.
Yeah, it's not so boring.
It's so hard.
Why? Because you don't like taking square roots of complex numbers?
Yeah, how do you even do that?
We'll look at that at the next video. But one thing I want to say is, what happens if you get a really, 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 really good conductor, like sigma goes to infinity?
Wow, what would happen?
Yeah, what would happen?
Well, before we think about that, let me Google how to do complex numbers. I'll see you later.
Okay, next video.